We have a slightly more complex circuit here. Here's the battery with an EMF of 12 volts. Then coming out of the positive terminal of the battery, here's your first resistor, R1 at 3 ohms. Then coming out of the first resistor, we have a junction here where we have two resistors in parallel, R2 and R3. I gave them both the same resistance, 2 ohms apiece. So the charges, the current will split up right here. Some of it will go through R3, some will go through R2, come back together to this point here, travel along to this next set of resistors. So this set of parallel resistors here, R2 and R3, they are, again, they're in parallel, but together they are in series with R1, and they are in series with R4-5. Notice R4-5 are also in parallel with each other, but this unit is in series with that unit, which is in series with R1. So we have a more complicated circuit. I want to figure out the equivalent resistance, EQ for equivalent, that's the lowercase eq, or effective resistance, equivalent resistance of the entire circuit. Once we know the equivalent resistance of the whole circuit, we'll be able to figure out the current coming out of the whole circuit. So how much current does the entire circuit draw? Whatever current comes out here is the current that goes through R1. That'll allow us to find the voltage dropped over R1. And then just to continue this on a little bit, we'll figure out the voltage dropped over R2, and then the current that goes through R2. And that will be enough of this exercise. All right. So to find the equivalent resistance, so this R1 is in series with that whole thing, which is in series with this. So the way to do this, we have to break these down into more manageable circuits. So I can find the effective resistance of R2 and R3, all right, which are in parallel. Once I figure that out, and I'll do the same thing for R4 and R5, then it will be, so I'll have R1 of 3 ohms. I'll find the effective resistance of R2 and R3. Whatever that number is going to be in series with R1. I'll do the same thing for R4, R5. It'd be like eventually having 3 resistors in series. Okay, so let's find the effective resistance of R2 and R3. Those are in parallel with each other. So I'm going to label that R23. All right, 2, 3 for resistors 2 and 3. So in parallel, so that's 1 over R2 plus 1 over R3, which would equal 1/2 plus 1/2, which of course is 2 halves, or 1. Remember that it's going to be 1 over 1. I mean, honestly, you don't have to write that. But remember, if it weren't anything other than 1, it's the reciprocal. This is 1 over R23. You want to know what R23 is, and that's going to be the reciprocal of 1, which is 1 ohms. Okay, so the effective resistance of this section right here is 1 ohm. What's the effective resistance of this? So that's 1 over R, what I'm going to label 4-5. That's going to be equal to 1 over R4 plus 1 over R5, which is going to be 1 over 4 plus 1 over 4, which is 2 over 4, or 1/2. Put that down here. So yeah, 1 over half, that shows up. Which means that that's 1 over the resistance. So to find the effective resistance of 4 and 5 in parallel is going to be the reciprocal of 1/2, which is 2 ohms. So you could redraw this circuit like this. I'm just going to do this briefly, then I'll erase it in a second. So This is your 12 volts, your EMF. This is R1, which is 3 ohms. This is R23, which is 1 ohm. All right, this whole thing is 1 ohm. And notice that it's down. This is downstream of that. And then this is downstream of this one. And R45 is 2 ohms. And so this is R45 of 2 ohms. So now you can find the effective resistance because you've simplified this so that they're all in parallel. I'm sorry, they're all in series. So 3 ohms, you know that for in series you just add them up. So to find the effective resistance of this circuit, because it's now a series circuit, it's going to be R1 plus R23 plus, that's awful, sorry, plus R45. So that's 3 plus 1 plus 2 is 6 ohms. So that's how we find the overall resistance of the circuit. Okay, so this came out to be 6 ohms. I'm going to erase this because I need the space. I'm going to write these values over here. So R23 is 1 ohm. That's the effective resistance of this unit. And R45 we found to be 2 ohms. Again, that's the effective resistance of that whole unit. And then I'm going to erase all this. All right, so to find the current coming on the entire circuit, again, we're going to ignore any resistance in the battery. So we're going to assume that we actually get 12 volts out of the entire battery. The EMF is 12 volts. That's going to equal I for the entire circuit times the equivalent resistance. Again, this is just Ohm's law. For those of you that are in the AP class, this would, in truth, be the terminal voltage, delta V subscript T for terminal. Remember, you get a little less out of the battery when you have a current going through it. But anyhow, we're kind of simplifying and idealizing the situation. So that's going to be 12. That's I for the entire circuit. And then we came up with 6 for this, right? So I comes out to be 2 amps. So you have 2 amps coming out of the circuit. So the 2 amps comes out of the circuit. So you have 2 amps that goes through R1, all right? And that allows you to find the voltage dropped over R1. So delta V1 equals the current that goes through it times R1. So that's 2 times 3 ohms is 6 volts. So of the original 12 volts, that's over the entire circuit. You have this 12 volt gain in the battery. 6 volts are used up over R1, leaving 6 volts to be used up over this whole thing right here. When you have circuits in parallel, we know that we have 2 amps coming into this, right? You have 2 amps going all the way through here. It'll split up at this junction. Some will go through here, some will go through here. Then they'll come back together again, and you'll have 2 amps again right here. Split up here, and then come back together again as 2 amps. Okay. But you don't get, so it's going to split up. You're not going to get all 2 amps going through here. Some of it will go through R2, and that's what I'm looking for right down here. Some of it's going to go through R3. In fact, because they have the same resistance, they're going to split up equally. If the resistances were different, they'd split up differently. I can figure out the voltage dropped from here to here because I know the equivalent resistance. And remember the voltage, you have an energy drop. Voltage is related to energy. You have an energy drop from this point. The energy drop from this point to this point is the same whether the charges go through R2 or go through R3. It's the same energy drop, okay, from that point to that point in this loop. Okay, so I know that the effective resistance from this point to that point is 1 ohm. I know that the overall current that goes through this entire R23 is 2 amps. And so I can find the overall voltage drop over R23 is going to equal the current that goes through the entire thing times the overall resistance. Okay, again, I know the current splits up, but if I look at it, if I treat it like an effective resistance of R23, treat it as a 1 ohm overall resistance, where I know that 2 amps goes through the whole thing, I can calculate the overall voltage dropped. That's 2 times, well, that's 1. So we have 2 volts. So I know that 2 volts is dropped from this point to that point. We started out with 12. We dropped 6. So we started out with 12 volts. And then we go over that. So now we've just dropped 6. And now we just dropped from this point to here, we just dropped 2 more. So there's a drop from here to here of 2 volts. By the way, so we 12 minus 6, we're down to 6, minus 2, we have 4 volts left. So what's the drop from here to here? 4 volts. Because they have to add up to 12. 12 minus 12 minus 6, that's 6. Minus another 2. And then whatever's left over when you come back down over to here, because this is 0. Right, that's 0 volts, that's 12 volts. Okay. The very last thing, before I run out of time, what's the current going through either one of these things? I chose R2. Now that we know that you've got 2 volts from here to here, whichever way you go, you lose 2 volts. From here to here is a loss of 2 volts, from here to here is a loss of 2 volts. This thing about voltage, it's the same in parallel, from here to here or from here to here. Knowing that, delta V2 is 2 volts. And using Ohm's law, delta V2 equals I2 times R2. Well, that's 2 volts. And the resistance happens to be 2 ohms. And so I2 is 2 over 2 is 1 amp. Okay. So of the 2 amps, this isn't any surprise, but of the 2 amps, 1 amp goes through R2, 1 amp goes through R3. Again, that they split up equally because the resistances are equal. All right? If the resistances were different, they'd split up differently. They come back together again, and then you could do the same analysis on this last set of resistors, but I'm not going to go through that. Okay. So that's how you handle more complicated circuits. It's a bit of a puzzle. You know there's an answer to that puzzle. It's a bit of a puzzle, and you need to simplify it. In this case, I took the smallest units that were parallel and found the effective resistance, equivalent resistance for each small unit, and then we're able to treat them as if they were like 3 resistors in series to find the equivalent resistance. Then I found the current coming out of the entire circuit, and then I was able to go back and figure out some of the smaller pieces, such as the voltage dropped here, the voltage dropped here, the current going through there. And if we needed to, we could have found power over any of these individual things now that we know the currents and the voltages. All right.